Hello, everybody, and welcome to lecture today. Today is the 15th of April, and today we're going to be talking about, we're skipping 3.4 and 3.5, and we're going to be talking about 3.6, rational functions. Okay, so the rational function, we've talked about rational expressions, remember? So these are just rational expressions expressed, or, used in as functions. So, whenever there's been like a common theme with these functions is we try to find their domains, their range, what the end behavior of functions look like, even or odd functions. So we're now going to do that with rational expressions, especially now that we've learned how to divide polynomials. Okay, so it starts out with the fact that if you add with polynomials, if you add them, multiply them, and subtract, add, multiply, and subtract. Polynomials. Okay, so if you add two polynomials together, it stays a polynomial. If you multiply two polynomials together, it stays a polynomial. And if you subtract two polynomials, one polynomial from the other, you get a polynomial. Okay? The case is different for division. Division, you may not get a polynomial. Okay. So that's the idea. And we've actually, so that last chapter, section 3.3 we learned was just about dividing polynomials. So a rational expression, it fits very nicely into this discussion. Okay, so so here's some examples of the types of functions I'm talking about. We're not doing anything with them, just looking at what they could be. So f of x equals x minus 1 over 2x plus 1. So that's an example of a rational function. Okay, because we have a polynomial up here, x minus 1, and down here we have 2x plus 1. Another polynomial, okay? You could have g of y equals 5y over y squared plus 1, or you could have this one. Okay, so this one, all polynomials are actually rational functions too. The polynomial on the bottom here is just 1. Okay, so polynomials just take this form here. Rational expressions rational functions rather are f of x equals the numerator oops, over the denominator. Okay, so these two are just polynomials. And the domain is all numbers where d of x is not equal to 0, right? So all the times where you don't divide by 0. Okay, so like, for example, this polynomial, or this rational function here, its domain would be everything except for negative 1/2, because if you put in negative 1/2 right here, you get 2 times negative 1/2, which is negative 1 plus 1, and you'd be dividing by 0. Okay? Here, this one, there's no way I can get a negative number out of a y squared. So this one's domain is actually also negative infinity to infinity. Or not also, but differing from this one. And this one, there's no way that the denominator can ever be 0 if it's 1. So, and that makes sense because this is a polynomial, and we know the domains of polynomials are from negative infinity to infinity. Okay? So, so there's also 3 different types of domain examples there too, which is something we will talk about. It's actually the first thing we will do, is talk about the domain of our rational functions. Okay, so let's find the domain of f of x equals 3x squared minus 12 over x minus 1. Okay. So according to our notes up here, rational functions are in this form, and the domain is the domain is all real numbers where the denominator is not equal to 0. So if we want to see where the denominator is not equal to 0, it's the same thing as if I solve this denominator here, x minus 1, for 0, and then just excluded those numbers. So I'm going to take the denominator, x minus 1, and set it equal to 0. So this is x equals 1. So the domain is just x cannot be equal to 1. Or you can write that as negative infinity to 1 excluded, union, right? Union or is also or 1 to infinity. That's just, these are 2 separate ways of writing a domain. Okay? So that would be the domain of that rational function. So the next one I want to talk about is g of x equals x divided by x squared minus 6x plus 8. Okay, so now we need to look at the zeros of this denominator. So we have to set x squared minus 6x plus 8 equal to 0. Okay, so this is a factoring question. So now we can factor this here. So this is going to be x, and I need to get 2 numbers that multiply to positive 8 but add up to negative 6. So I'm going to do minus 2 and minus 4. Okay, so I need to solve x minus 2 equals 0 and x minus 4 equals 0. So this one is x is equal to 2, and this one is x is equal to 4, right? Add 2, add 4. Okay, so these are the domain. These are the values that x cannot be, so the domain is x not equal to 2 or 4. You can also write that as negative infinity to 2, exclude it, 2 to 4, exclude, and 4 to infinity, exclude. Okay, let's do one more. So last example we have here is x squared minus 4 divided by x minus 2. So find the domain of this one. So this one, we would just set this denominator here, x minus 2 equal to 0. Okay, well this is just x equals positive 2. So this one's domain is x not equal to 2. You can also write that as negative infinity to 2, exclude, or 2 to infinity. Okay, so yeah, this is something we've actually, we've learned how to take domains of functions and take zeros of polynomials. So we've done this before. Okay, just a little review there. So now we're going to talk about, okay, so what actually does, what happens if I were to actually look at the graph of this function? What would happen at 2? Is it just going to be a little hole in the graph? Is it going to be a line, what we call an asymptote, that the graph never touches? We want to actually see what kind of behavior this is. Okay. So a vertical asymptote is what I want to introduce next. So a vertical asymptote is when, if you consider I'll show you an example of it first. So the function f of x equals 1 over x. Alright. So I'm going to draw this graph. Okay, so the graph of 1 over x looks like this. That's our graph here. So this is x and this is y. So the reason, you might notice here that this is not a continuous function, right? Because I can't draw it without picking up my pencil. And the reason it's not continuous is because it never touches 0 here. So you can't put 0 in here. You can't divide by 0. So that's why this right here is what we call a vertical asymptote. In this function, it just coincidentally happens to be the y-axis, because the graph of the line, the vertical line, never touches it, and it just continues to approach it. Okay? So you might see that too, is if I put, let's say, if I do f of 0.5, then this is equal to 1 over 0.5, which is equal to 2. So here's 1, right? And that's also 1. So if I plug in 0.5, I'm already up to 2. And the closer and closer I get, right, if I make this number here in the denominator even smaller, like 0.01, that's 1 divided by 0.01, which is the same. 0.01 is equal to 1 over 100, right? But then dividing a fraction by a fraction, this is the same thing as multiplying by the reciprocal, so this is equal to 100. So as soon as I'm down to 0.100th, I'm already up. The height is way off this page. So it's just saying that the closer and closer this number gets from the positive side of x equals 0, right? The closer it gets to 0 from approaching from the positive side, the closer it just goes to infinity. But it never does actually reach, you can never actually plug in 0, because then you'd be dividing by 0. Now, however, on the left-hand side, if I plug in f of negative 0.5, you get negative 2, just like you did up here, except with a negative. And if I plug in f of negative 0.01, this would be negative 100. So for the same reason that this one's shooting off to infinity as you approach from the positive side, this one's going to shoot off to negative infinity because the number just gets really, really small. The output gets super, super small, super negative. Okay, so that's what a vertical asymptote is. So you can have these in, these can appear this one just coincidentally happens at the y-axis or when x is equal to 0, but you could, for example, have a vertical asymptote at x equals positive 2. It depends on the function. So some notation you need to learn here that the book uses, and I'm sure will pop up on your homework. We already know that these arrows, so x going to a plus. So this little plus right here, remember the arrow's talking about, we used to do as x goes to infinity, but now we're saying, okay, as x approaches a number. In our example here, this is going to be like x approaching 0 from the right. So x approaching 0 from the right is you start from the right of 0, of x equals 0, and you approach x equals 0 from the right. So if I would have just said x equals 0 without the plus, that actually is in two different directions. So this is just specifying what side I'm approaching. Okay, so you can do the same thing with x approaching a from the right. Okay, this one, x approaching a left, is the same thing, x approaching a from the left. Okay. So that would be going like this, because you start from the left of your number and approach x equals 0 from the left. Okay, so then we already know what these two, we've seen what, f of x goes to infinity, or f of x goes to negative infinity. So in this example, I would say as x goes to a positive, so as x approaches 0 from the right, our function f of x approaches positive infinity, because as x gets closer and closer to 0, f of x shoots up towards infinity. So you could also say that as x approaches 0 from the left, so I should say 0 here. As x approaches 0 from the left, f of x goes to negative infinity. Okay? And that's precisely what it takes to have a vertical asymptote. So let's kind of define that. Not kind of. Let's define what a vertical asymptote is. So the line x equals a, in our example it was x equals 0, right, is a vertical vertical asymptote of the function f if f of x goes to infinity as x goes to a positive, or as x goes to a negative, or f of x goes to negative infinity as x goes to a plus, or as x goes to a minus. Right, so in our case, our last example, we had this situation. We had as x goes to approaches 0 from the right side, f of x went to positive infinity. We had x going to 0 from the right, and f of x going from and f of x going to infinity. So note that we also had another case, but it just happened to be at 0. So as x went to 0 from the left, this one, we got f of x equals negative infinity. But again, it can happen. You can have, if you just put a negative out here in front, this graph would flip. It would this side would come down here, and this side would flip up here. So you could have the opposite situation. Right? So that's why we have to include these two others. Okay, so that's what it takes to be a vertical asymptote. So now let's describe a horizontal one. Horizontal asymptote. Okay, so first off, I'd like to say that the horizontal or the vertical asymptotes, the lines going vertical in the graphs, can occur at any x value, right? So sometimes we have to look. It just depends on what the output really does here. So in the horizontal asymptotes, you really have to look at the end behavior, which is something we've already actually done. And I'll show you why. So again, consider f of x equals 1 over x. So I'm going to bring back my picture that I've already drawn here and copy it. This one's not quite as good. Okay. Okay. So the horizontal, notice that there's also a horizontal line here, the y-axis, that is never touched by the function. So that's actually a horizontal asymptote, unlike a vertical asymptote, can actually touch the function, but it really just depends on what its end behavior is. Okay, so there are a couple types of horizontal asymptotes. There's this one, right, where it can come from the positive and just approach the number here. There's this one where it can come from below and approach the same number from below. Then there's the cases where you can have a function come down like this. And it can touch it, infinitely many times, but it's still just getting smaller and smaller towards that number. Okay, and there's the same case where you could have it go so and oscillate on the other side. Okay, so the thing is we have to look at what exactly happens as x goes to infinity, because the horizontal asymptotes have to, they have to be vertical lines that go that stretch this whole x axis. So we have to look at the end behavior, or when x goes to infinity, or when x goes to negative infinity. So the horizontal asymptote, so in this case, the end behavior, if I let x get really, really big, like go to positive infinity, as x goes to positive infinity, then it's just this, the bigger and bigger x gets, the smaller and smaller 1 over x gets, because you're dividing by a bigger number. So it's really looking like f of x goes to 0. As x goes to infinity, f of x goes to 0, right? As x gets really, really large, this number is just going to keep getting smaller and closer to 0. It's never going to be negative, though, because it's never going to cross it, but it's going to get really close to 0. So same thing on this side. What about as as x goes to negative infinity? Then f of x goes to 0, except it just goes to, it gets really, really close to 0 from the negative point of view. So if I put in a really big negative number here, it's going to be really close to 0, but it's going to be negative. Okay, so this x equals 0 is a horizontal y, the line y equals 0. It's a mistake on my part. Y equals 0 is a horizontal asymptote. Okay. So the definition then is going to be the line y equals k is a horizontal asymptote of the graph of a function f if f of x goes to k as x goes to infinity, or as x goes to negative infinity. Okay, so the vertical asymptotes depend on your discontinuities, so those x's where you set the denominator equal to 0, and the horizontal asymptotes depend on just the end behavior of the function itself. So now we're going to go ahead and put those two together, and we are going to look at some other functions, not 1 over x, but in similar form, and find their vertical and horizontal asymptotes. So let's do a couple examples. So what if we had, so this one says find vertical asymptotes and horizontal asymptotes. So I'm abbreviating now because I don't want to keep writing that. Okay, so here we have a equals negative, this is not a, problem a, f of x equals negative 2 over x plus 1. They want us to find the vertical and horizontal asymptotes. So here it turns out, so let's find the vertical ones first. So vertical ones, the vertical asymptotes, we look at the denominator equal to 0. So we're going to set x plus 1 equal to 0. Okay, so it turns out that this might not have to be to find the vertical asymptotes, you have to make sure that there are no x plus 1 factors up in the numerator to cancel with this. So I'll explain that. That actually comes later in the section, but there is one extra step you actually have to do for any general function. But this one has a degree here that's bigger than, or there's no common factors of x plus 1 in this one. So we can go ahead with this process. So this is just x equals negative 1. So this is going to be a vertical asymptote, because if I let x go to negative 1 from the right, or from the left, so I put an x goes to negative 1, and then this little minus up here signifies from the left. Anything a little bit bigger than negative 1, like a little bit smaller than negative 1 is going to be like negative 1.1 or negative 1.01. Anyway, it's still going to be something a little bit bigger or a little bit smaller than negative 1 plus 1. So this on the bottom is going to be a negative number. And this is also a negative number up here. So this is going to say that f of x approaches, but this is a negative constant number, and this is going to be like, this sum here is going to get closer and closer to 0, but it's going to be negative. So negative divided by negative is positive, but the number itself is going to become very large. So this is going to be, as x approaches negative 1 from the left, the function goes to positive infinity. So we already have one of the definitions for a vertical asymptote. So again, if we because let's see what it does as it approaches from the right. So as it approaches negative 1 from the right, aka negative 0.999999, negative 0.99999, the more and more nines you can add on there. Either way, this is now going to be a positive number that's getting very, very small and like close to 0, and this is a negative number that's constant, so this is going to mean that f of x goes to negative infinity. So yes, we have actually, our definitions for vertical asymptote are satisfied here. So now we've identified that x equals negative 1 is a vertical asymptote. So now let's find the horizontal asymptote. So we need to look at x going to infinity. What does f of x do? Okay, so as x goes to infinity, f of x equals negative 2 over x plus 1. So if I put a very, very large positive number in here, it's going to be a constant negative number and a super large, a very large positive number here. So negative divided by positive is positive, but it's going to approach 0 as x goes to, because you're getting this constant negative 2 divided by an extremely large number, so it's going to get very close to 0. So yes, as x goes to infinity, f of x goes to 0. Okay, so what about if x goes to negative infinity? Well, you can also, this is kind of incorrect to do, but you could also write in infinity plus 1. And you would see that this is a very large positive number, and this is a negative number, but it's still going to be going to 0, because when we talked about end behavior of functions, we need to look for the sign, and we need to look for the actual number it's going, the absolute value of the number it's going to. We also talked about end behavior where this is a degree 0 polynomial and this is a degree 1 polynomial, so the denominator would get larger much faster because it has a higher degree. So that was in the end behavior section of chapter 2. So now if x goes to negative infinity, we get kind of a negative 2 over negative infinity plus 1. So this is really going to grow the same as negative 2 over negative infinity. That plus 1 doesn't, negative infinity plus 1 is still negative infinity. But these will cancel off, and that's going to go to 0 as well. So we have a if x goes to negative infinity, f of x also goes to 0. So then there is a horizontal asymptote at y equals 0. So up here we also should have wrote vertical asymptote at x equals -1. So that would be how you find vertical and horizontal asymptotes of that polynomial. So, or of that rational function. So let's do another one. Let's do 3x minus 2 divided by x minus 1. So again, the vertical asymptote will go first. So we set d of x equal to 0. So x minus 1 equal to 0. Then we add 1 to both sides to solve for x. So that's our vertical asymptote candidate here. So if I approach x equals 1 from the right, if I let x go to 1 from the right, then it's going to be like 1.0001 anyway, and get closer and closer to 1, but only from the right. So only numbers that are actually bigger than 1. So then only numbers that are slightly bigger than 1 minus 1 is going to be a positive number, but it's going to be extremely small, but it will never be negative. Okay, so it's going to be a small positive number. And then up here we have 3 times 1 minus 2. So that's just 1, but it's a constant. So we're going to get 3 times 1 minus 2 divided by something positive, but very small. So that's going to go to infinity, because if you have a constant number 1 divided by a very, very small positive number, you have a positive divided by a positive, and then 1 divided by extremely small numbers, as we saw before in the example 1 over x, goes to positive infinity. Okay, if I let it go from x from the other side, as x goes to -1, we have 3 times -1 minus 2 over a negative sign now, right? Because it's only numbers that can be smaller than 1. So like 0.9, 0.99, 0.999. Either way, this number that's on the left of 1 minus 1 is going to be negative, but very close to 0. So it's going to be negative, very small. This one, 3 times -1 minus 2 is going to be also negative. Okay, yes. Actually, this is still a 1. So what happens here is we're letting x go to 1 from the left. So it's still going to 1, so it's going to go to like 0.9, 0.999. So this is still going to go to positive 1, but 0.9, 0.99, 0.999, whatever very number you put very close to 1 from the left, minus 1 is going to be negative. So this is going to be a 1 over negative something very small, which is negative infinity. Okay, so we have a vertical asymptote at x equals 1. Now horizontal asymptote, we have to look at x going to infinity, the end behavior, and x going to negative infinity. So of 3x minus 2 over x minus 1. So looking at the end behavior here, we learned that if we have the same degree, a couple sections ago, if we have the same degree number, or same degree polynomial over the polynomial that has the same degree, then we need to look at the leading coefficients. So this polynomial is a degree 1, and this one is a degree 1 polynomial. So we need to look at the leading terms, so 3x and x, and then their coefficients, so 3 and 1. So this one goes as x goes to infinity, we have that f of x goes to 3, or 3 over 1. So the same thing here, because if I plug in a negative infinity up here and a negative infinity right here, those negatives will cancel out, and so as x goes to negative infinity, f of x goes to, so I should have wrote an arrow here, goes to 3. So, right, so because I can treat, you can treat, so the way this really works is, if I'm going to manipulate this over x minus 1, manipulate this a little bit. I'm going to multiply each, I'm going to multiply the top and bottom of this fraction by 1 over x. Okay, so this is going to be 3x over x minus 2 over x divided by x over x minus 1 over x. So if I let x get very, very large, these two cancel out and this cancels out. So this is really like 1 minus 2 over x divided by 1 minus 1 over x, because x over x is 1 and 3x over x is 3. So this should be a 3. Okay. So if I let x become very, very large, then 2 over a number very, very large is like 0, and then this one is also, this number here goes to 0 and this number here goes to 0. So this, as x gets very, very large, positive or negative, we get the behavior of 3 over 1 or 3. So there's a horizontal asymptote at x equals, y equals 3, sorry. Okay, so that's how you find vertical and horizontal asymptotes. So a general way to do this is, if nx over dx equals f of x, and nx and dx have no, wow, I wrote that very, and dx have no common factors, then if a is a factor of dx, then x equals a is a vertical asymptote of f of x. So this kind of theorem here saves us the trouble of having to check if it's a vertical asymptote with the other definition. So if I look back at these examples, finding the vertical asymptote of negative 1 here, I wouldn't have had to do all this check. It would just say, because nx equal to negative 2 and dx have equal to x plus 1 have no common factors, right? I can't pull an x plus 1 out of the numerator, then there's a vertical asymptote at x equals negative 1. Okay, so let's do a couple here. So we would just have to do f of x equals 1 over x minus 1. So 1 and x minus 1 have no common factors. So this one would have a vertical asymptote at x equals positive 1, because I would just add 1 to both sides. So if we had g of x equal to 1 over x squared minus 9, then x squared minus 9, this can be factored into x plus 3 and x minus 3. And x plus 3, there are no x plus 3's and x minus 3's up in the numerator, so there's no common factors. So there's vertical asymptotes at x equals negative 3 and x equals positive 3, because if you solve x minus 3 equals 0, it's x equals 3. You solve x plus 3 equals 0, x is equal to negative 3. Okay, another type is if you have h of x equal to 1 over x squared plus 1. So you can't factor this. This is non-factorable, and actually this denominator doesn't equal 0 ever, because a number squared can never be negative, right? I can never get a negative 1 to cancel with this positive 1 to divide by a 0. So this one has no vertical asymptotes. So just put VA. Okay? All right. So now we're going to talk about what if they do have a common factor. What if there is a common factor? So this is what you call a whole. Functions whose graphs have functions whose graphs have holes in them. Okay, so the first example is, let's say we had h of x equal to x squared minus 9 divided by x minus 3. So if they wanted you to find the vertical asymptotes, then you first would have to check if there's any common factors. So I would factor this. So this turns into an x plus 3, x minus 3 divided by x minus 3. So we see that we have a common factor here. We can cancel this out. So this is equal to x plus 3 if x is not equal to 3. Right? Because if I go back to the original equation, if I plug in a positive 3 here, I'd get a division by 0. And you can't have that. So actually, x, because x minus 3 is a common factor, x equal to 3 is a whole in f. Well, the graph of f. Okay? So anytime you have a common factor and you cancel out like that, you still get a hole in the graph. It actually becomes a non-vertical asymptote. So like for example, what if I graph this x plus 3 if x is not equal to 3? X plus 3 if x is not equal to 3. Well, it's a simple graph. It's actually 1, 2, 3. So 1, 2, 3, 5, 6, 7. So if I'm at 1, I go 1 plus 1, 2, 1, 2, 3, 4. I need 1 plus 3, so it would be here. And goes up 1 over 1, up 1 over 1. So 1, 2, 3, 4, 6. So at x equals 3, though, we need to draw a little whole because we're graphing x plus 3 except for when x is equal to 3. So that's what our graph looks like. It's just the function with a hole at 3. Because we had when we have this cancellation, we have to write, okay, this is equal to x plus 3 except for when x is equal to negative 3 because we canceled here and we can't divide by 0. Okay, so that's what a hole in the graph looks like. So what about this example? We have x plus 2 divided by x squared minus 4. So this is equal to x plus 2 over x plus 2, x minus 2. So these guys cancel out. So this is equal to 1 over x minus 2, except when x is not equal to 2. Negative 2, sorry. So we'd have a vertical asymptote, or we'd have a hole at x equal to negative 2, and then in this example it factors down to 1 over x minus 2. In this other one it factored down to x plus 3, just a linear equation. This one is a rational expression itself, which has a vertical asymptote at x equals positive 2, because that's when the denominator is equal to 0. Okay, so it has a hole at negative 2 and a vertical asymptote at positive 2. Okay, so that's the difference between a hole and a vertical asymptote is the common factors. If you can cancel them out, it's a hole, and if you can't do that, if it's only a factor of the denominator, then it's a vertical asymptote. Okay, so there's like a table of rules here for identifying this stuff. So rules for locating. Rules for locating horizontal asymptotes. So those are how you find holes in vertical asymptotes. Horizontal asymptotes are a little different, right? Okay, so you want to f of x equals nx over dx, where the degree of n is equal to little n. So it's a degree little n polynomial. The degree of d is equal to little m. So there's three cases. You could have the degrees m equal n, the degrees would be the same. The degree of the numerator is bigger than the degree of the denominator, so n would be greater than m, or the degree of the denominator is greater than the degree of the numerator. So because this all is based on n behavior, which we've talked about, so 1, if little n is greater than little m, if the degree of the numerator is bigger than the degree of the denominator, then the x-axis is the x-axis, which is y equals 0. The horizontal asymptote. Okay. So 2, if n equal m, then the line y equals, so this is the leading coefficient. So right, if it's a degree n, little n, then nx is equal to a n x to the n plus dot 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 plus a1 x plus a0. This, if degree m, this is a m x to the m plus dot 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 plus a1 x plus a0, right? So, okay, so technically I should call these b's because they're different numbers. Okay, so, but it's still the same idea. B, B, B0. And this would be a BM. So it's AN over BM is the horizontal asymptote. So this table is on page 391. Okay. And last, if oh, sorry, I screwed this up. So this is the case if n is less than. So if the degree of the numerator is smaller than the degree of the denominator, then the x-axis y equals 0 is the horizontal asymptote. If they're the same, that's true. Then an the leading coefficients is a horizontal asymptote. If they're last but not least, if we have n greater than m, then the graph either has no, or has, sorry, shouldn't put the either there. I'm changing this a little bit. Has no horizontal asymptote, but may have an oblique asymptote. And we'll talk about that a little later. But right now you just have to be concerned with that it has no horizontal asymptote. Okay, so here let's use this to see if we have horizontal asymptotes. So f of x equals, so find HA 5x plus 2 over 1 minus 3x. So find the horizontal asymptote. So this is a degree 1 polynomial, and this is a degree 1 polynomial. So m equals n. So we have to look at our m equal n, which these are equal to 1, by the way. So if n equals m, then we have to look at an and bm. So we have to be a little careful here because, right, we want to look at 5x plus 2. We have to put these in standard form, 3x plus 1. Or you just have to notice that negative 3 is bm and it's not positive 1 because 3 is going with the x. So we look at these leading coefficients, so it's equal to 5 over negative 3. So y equals 5 over negative 3 is a horizontal asymptote. So this should be an arrow. Right. Okay, so that's how you do it for that one. So what about a different example? G of x, 2x over x squared plus 1. So 2x over x squared plus 1, this is degree 1, so n is equal to 1. And this one is degree 2, m equals 2. So this is the case where n is less than m. And if n is less than m, the first case, then the x-axis y equals 0 is a horizontal line. So y equals 0 is h, the horizontal asymptote. Okay, so finally, let's maybe do one with the third case. So h of x is equal to 3x squared minus 1 divided by x plus 2. So 3x squared minus 1, this is n equals 2, the degree of the numerator equals 2, the degree of the denominator equals 1, so n is greater than m. So this one is this case. Then the graph has no horizontal asymptote. No horizontal asymptote. Okay, so that's how you find horizontal asymptotes in general. So now we're going to go ahead and talk about graphing. We're going to do one example of graphing and then come back to this tomorrow. So if I want to sketch a graph of f of x equals 2x squared minus 2 divided by x squared minus 9. Okay, so if I wanted to sketch a graph of that, I need to first find HA and VA. So first I'm going to check for the vertical asymptote. So I'm going to completely factor these two. So I can factor this as 2x squared minus 1 divided by x plus 3 times x minus 3. So this is f of x. So this is equal to 2 times x minus 1 times x plus 1 over x plus 3 times x minus 3. Okay. So to find the vertical asymptotes, we first check, are there any common factors that I can cancel out? Because those would be holes in the graph rather than vertical asymptotes. No. Okay, so no common factors. No common factors. All right, so from the vertical asymptotes, then that says that our little vertical asymptote rule, x equals negative 3 and x equals 3 are vertical asymptotes. All right, so now let's find the horizontal asymptotes. So we have if we go back to the original form, we have a degree 2 polynomial here and a degree 2 polynomial here. So we need to look at the leading coefficients. So I should have circled this. 2 over 1. So since m equals n equals 2, a2 over b2 equals 2 over 1. The leading coefficients are 2 over 1, so that's equal to 2. So we have a horizontal asymptote at y equals 2. Okay. Now just like when we're graphing other functions, we want x-intercepts and y-intercepts. Okay, so x-intercepts, we set f of x equal to 0. So x-intercepts are 0 equal to x minus 1 times x plus 1 divided by x plus 3 times x minus 3. So a fraction can only be 0 when its numerator is 0. So we set 2 times x minus 1 times x plus 1 equal to 0. And divide both sides by 2, so x minus 1, x plus 1 equals 0. So either x equals positive 1 or x equals minus 1. So these are the x-intercepts. Okay, so the y-intercept is found by you set x equal to 0, so it's just the y-intercept is equal to 2 times -1 times, right, 2, putting 0 in here for x, 2 times -1 times +1 divided by 3 times -3. So that's going to be -2 over -9 or +2 over +9. So that's the y-intercept. Alrighty. So now the next step is if we start to draw this graph, we have a slight problem. So I know, for example, that the point 1, 0, that's on the graph, that's an x-intercept, and so is -1, 0. So those 2 points are on the graph. And so is 0, 2/9. Right? So those 3 points are on the graph. And I know that the graph has a vertical asymptote, or horizontal asymptote at y equals 2. So I can draw this dotted line. Horizontal asymptote, y equals 2. And it has 2 vertical asymptotes at 3 and -3. Okay? So we found out all that information. So now I need to I can look at the I need to look at the behavior. Is this a vertical asymptote where it's going to approach -infinity on the side of 3, on the side of -3? Is it going to come down like this, or is it going to go up like this, right? And is it going to be on the positive side, or the lower side of our horizontal asymptote, or the upper side of our horizontal asymptote? Okay, so the idea is you use test values. So you use polynomial division too. So I take the original f of x, and it equals 2x squared minus 2 over x squared minus 9. So using long division, I'm going to divide this. So this is going to be 2x squared minus 2, and then an x squared minus 9. So I just need to multiply this one by 2 to get a 2x squared minus 18. So now I'm ready to subtract those off. So this is a 0, -2 plus 18 is plus 16. So now my degree of a polynomial here is less than this one, so I can stop. So this f of x is also equal to 2 plus its remainder, 16, divided by the divisor, x squared minus 9. Quotient, remember this is q of x plus r of x over d of x. From last section. Okay, so now it's actually kind of nice, because then I could figure out that so it turns out that when you have a horizontal asymptote, this is going to be your y equals k. Q of k is equal to q of x is equal to when there is a horizontal asymptote. So when there is a horizontal asymptote, this is going to be your horizontal asymptote, which it did turn out it's 2. That's what our horizontal asymptote was. Okay, and that's because of the fact that to have a horizontal asymptote, you either have to have the degrees of this be the same, or the degree of the denominator greater than the numerator. Okay, so in this case, we see that if we were to rewrite this function as f of x minus 2 is equal to 16 over x squared minus 9, then this is saying f of x minus 2, so our function value minus the horizontal asymptote is equal to this function right here. Our function value minus our horizontal asymptote is equal to this function right here. So if I put in a number bigger than on this side, if I put in an x value where, if I wanted to see if the difference between my function values, my outputs, and my horizontal asymptote were positive, then it would be on this side of the upper side of the horizontal axis. If my function values in this interval minus the horizontal asymptote were negative, then they would be on the lower side of the horizontal asymptote. So you figure out in each of these intervals, you need to figure out what side of the horizontal asymptote you're on. So if I have f of x, if I take my test values, the test values are going to be in your at the vertical asymptote. Okay, so you're going to test a value in the interval negative infinity to negative 3, negative 3 to 3, and 3 to infinity. Okay, so I would choose negative 4, 0, and 4. And you need to test if they're... Sorry, I'm not writing this down. So those are your test intervals because those are the intervals broken up by your vertical asymptotes. Then you choose test intervals, just like the test point method, to plug into R of x over d of x. So if I plug this into R of negative 4 over d of negative 4, well, that's equal to a positive, and if I square negative 4, that's 16 minus 9, that's a positive, so this is a positive number. So this is positive. If I put 0 in here, it's 16 over 0 minus 9, so this is a negative, and 4 is the same story as negative 4. So that means that on the interval negative infinity to 3, f of x minus 2, our function values from here on over to 3, our function values minus the horizontal asymptote are positive. So that means that we're on this side of the horizontal asymptote. So we can draw our first arrow there. Okay, so we also need to see as we approach, for the vertical asymptote, as we approach 3 from the left, we need to see what the end behavior is. So 3 from the left for the vertical asymptote is, if I plug in a number smaller than 3, smaller than negative 3 here, so like negative 4 or negative 3.1. If I square that, it's going to be slightly bigger than 9. So this is going to be a positive. It's going to be a positive number at when you approach 3 from the negative 3 from the left hand side. So x going to 3 from the left. Then the numerator is going to be positive, and the denominator is also going to be positive because negative 3 approaching negative 3 from the left. So then it's a positive over a positive, so f of x goes to infinity. So I know that it goes like this, so we can connect these dots, or connect those lines. So that's how we got our first line. So now if I want to see on this I know from our test here that on this interval, our vertical asymptote test, we say on the bottom side of the horizontal asymptote in between -3 and 3. So we're going to have but we also know that we have to pass through these 3 points. So it might kind of look like this. We also want to know where this comes from. So if it comes from we have to see where the behavior of the graph when x approaches -3. This is really tough. -3 from the positive side. Okay, so as x approaches -3 from the positive side, if I put from the right side, so I would be putting in -0.299, 2999, -2.999, that goes on and on. But it's going to be slightly less than 3, or slightly bigger than 3. So slightly bigger means, -2.9. It's weird because you're thinking about the negative side. But if I square that, it's going to be something less than 9. So this is going to be a negative. And again, putting -3 into the top here, I get a positive. So this is going to go down to, goes to -infinity. So that's kind of here. We can connect our curves here. So the same action goes, if I approach 3 from the left, I'm putting in +3, so x goes to 3 from the left. It'd be like 2.99, and the same story actually goes for this x goes to +3 from the left is going to be the same end behavior as x going to -3 from the right. So this one's going to go down this way. And then, again, those other two match up as well. So and I know that in this interval, I need to be below the horizontal asymptote. In these two intervals, I need to be above the horizontal asymptote because of this table down here. And then I just check the end behavior of, x. I just checked which way the vertical asymptotes are approaching by the same method that we did in the earlier examples. So that's how you can attempt to graph a function with by finding its vertical and horizontal asymptotes, and then the zeros and the y-intercept as well. So that's how you graph a rational expression. And we'll stop there and do a couple more examples tomorrow.